Okay, let's start. My name is Alfredo Ortega. I work as an Expl writer for core security. This talk will be about the OpenBSD bug. If you don't understand something that I am saying, just ask me and I will repeat. Okay. This is a bug that I discovered a couple of months ago, but like 4 months ago, and it's an interesting bug, and the exploit is interesting too, and got pretty much publicity, so I'm going to explain it. Okay. Oh. Let's start talking about how I discovered the bug. Okay, this is the history. This is the history. I was assigned to do a research about a patch in the OpenBSD kernel, named the number 8 patch, a reliability fix. This was, in fact, a hang of the kernel, an infinite loop in the kernel caused by fragmented ICMP packets. So my boss come and tell me if I could reproduce this bug. So I started trying to build a fuzzer. You know what a fuzzer is? It's a little program that sends malformer packets and try to break the system to reproduce the bug. So I really didn't have very much information about the bug, so the only thing that I could do is to start trying and studying the patch, trying to make a couple of fragmented packets and sending to our OpenBSD system, trying to make it to break, to lock in an infinite loop. So the fuzzer is a very simple program. I made it in Python. It only makes 2 packets from the IPv6 protocol. The IPv6 protocol is, as you know, a very new protocol. It's not very much used, and it's got a lot of bugs. I will be presenting this bug, and in the end, maybe I will do some live demonstration about another vulnerabilities. I spent about 2 days trying to building malformer packets, thinking how I could break the system, and in the end, in a lucky packet, managed to break the system. I sent it to an OpenBSD virtual machine, and the OpenBSD kernel just hung up. But it was not an infinite loop like the patch was seeing. It was a complete hang up. The system just hung up and threw a stack trace of the bug. I was thinking, this is not the same bug that I was trying to find. Maybe it's a new bug. So the thing that I did was to download the latest version of OpenBSD kernel. It was at the time the 4.1 OpenBSD kernel, and trying to attack against that kernel. The attacks worked anyway. So in my hands, I did have what is called a 0-day or a new unpatched vulnerability. In the time, I was thinking it was a Daniel service, and maybe it could result in code execution, but I was not really sure about it. So I reported to my boss. My boss reported to OpenBSD team, and got fixed in about 2 days. They were very fast and fixed the bug, but they reported it as a Daniel service of a reliability fix, and I was thinking that this was not a reliability fix. It really was an exploitable bug because of the stack trace. So I started researching how to exploit this bug. Let's see why the bug was hanging the kernel. Okay, these are, let's see, a lot of Unix systems, the network packets are stored in structures named MBUFs. The mbuffs are little packets of memory of a fixed length. They are about 256 bytes long. They are ordered in a linked list in memory, and they store network packets inside them. And if the network packet is too big to fit inside a mbuff, the mbuff got an external memory buffer. But the failure of the kernel was that the kernel was overwriting a lot of mbuff buffers in the way that is showing there. Instead of writing into the first mbuff, mbuff 1, the OpenBSD kernel was overwriting a lot of these buffers, and not only the buffer, but the header information inside the buffers and the couple of pointers that link the buffers, the linked list. So when the OpenBSD system was trying to free one of these packets, it made an unlink operation. That is, an unlink operation is an exchange of two pointers to free the node between them. And because of the pointer was overwriting with garbage, at the time was garbage, the system was hanging, was making an illegal operation, and it totally hung. This seemed like a very exploitable bug, because when you overwrite two pointers, you can use a very common technique named the mirror copy or forward write. When you exchange two pointers and you can control the pointers, you can manage to write 4 bytes of data in any place of the memory. So I was thinking, if I am overwriting a linked list, it's almost sure that it is an exploitable bug. So I started to disassemble the OpenBSD kernel to see if I could exploit the bug. Well, maybe you can, it's not showed very well, but here is a disassembly of the function that was hanging. The function that was hanging was a free function. I see in the down, the freem function was crashing. Here. The freem function was crashed. That is the function that free an mbuff. So I disassembled this function. That is the result. I must say that the OpenBSD kernel is an open source kernel, and I really did have the C code of the source code of that function, but I am really more used to see it this way, to see it in assembly, to analyze the function in assembly. It's more easy for me to see it this way. The function starts in the orange block, and we can see, if we could see it, maybe it's that the packet to free is stored in the register. I must clarify that this assembler is for the Pentium and 32 bits only. OpenBSD run in a lot of architectures, but this exploit is only for Pentium at 32 bits. Sorry. In the start, this function places the packet to be freed in the one register, in the ASI register, and then it made a lot of operation using this register as a reference. The point what the kernel was breaking is making in yellow. Is well, you can't see it very well, but it exchanges the pointers here in the block, making in the block painted in yellow. The pointers of the linked list are being exchanged, and of course the linked list was overwriting, and it was trying to write in a position of memory that did not exist. So it broke exactly in the yellow block. So I say, okay, let's try to reach the yellow block with controller pointers. So I can write in any place of the memory. If I can write a value in any place of the memory, I can do a lot of things, like make my user process root, or open, I don't know, change the permission of the new process. There are not very much things that I could do, but some things it could be done and it will be exploitable this way. And while I was analyzing this, I realized something. I realized that in the next block, in the block next to them, to the yellow block, was a call and the referencing a pointer. It was getting a pointer from the block here in the arrow in this part. Let's see. In this part is moving a value from the packet inside the EAX register, and then in the next block is jumping to this EAX register. In fact, it's calling them, but it's the same as jumping. So I could send a value here inside the packet and make that OpenBSD jump exactly what I want. So I can control the flow of execution in a much easier way than trying to do the other trick of the yellow block, that writing in some part of the memory. It's much easier to jump to any place that I want, because I could send my code and place my code or my shell code in some place of the memory and make the kernel jump it, and I will get total control of the kernel. Of course, I will gain execution inside the kernel, and it's not an ideal situation. The ideal situation was to gain control in a user process, because a kernel exploit is much difficult to do than a user exploit. Because in a user exploit, you got the kernel to do whatever you want. You can use the kernel to open a file or to open a connection. It's much easier. The kernel is made for that. When you do a user exploit, when only like 100 instructions, you can make the machine do what you want. It's a very small exploit. But in kernel mode, you really don't have a kernel. You don't have an operating system to make use of. So it's almost like you are your own operating system. Anyway, I was gaining execution inside the kernel, and I was executing my code. So I tell the OpenBSD people that in fact this bug was exploitable. I still didn't have the exploit. The exploit took me about a couple of weeks to make, because it was a very difficult exploit, and I was helped by a lot of people for kernel security. But anyway, now I am in the situation that I can jump to any place that I want in the memory, but where I want to jump. Of course, I cannot jump to the same kernel, because the same kernel is not my code. I want to jump to my code, so I can overtalk the system. First, I must place the code in memory in some way. Well, in this transparency, I have marked the source code in C, the equivalent of that function. Here's the assembly, and here's the part of the source code that make the call. It's a little difficult to understand. It's marked in red. It's marked the part of the source code that jump to the referential pointer. As you can see, it's much easier to understand in assembly than it is in C. It's a lot of micro expansions. I never will realize the bug looking only to the source code. Okay, that's better. Okay, in this drawing, you can see how the fragmented packets of ICMP v6 are placed in memory. In the right, we have the linked list of MBUF or MBUF chain with the corresponding headers. In the headers of the MBUF are pointers to the next MBUF, pointers to the last MBUF, pointer to the free function. And the packet are placed in exactly that way in memory, are overwriting a couple of MBUFers, or MBUF, and the arrow here, this arrow marks the exact position of where the pointer to jump is placed in memory. So I must place a pointer here, this pointer will overwrite the free function inside the header, and this function we call the pointer that I place there, here. Here is a trampoline. You can't really see it, but it's a trampoline. Trampoline is a name for a position of memory that I want to jump. I want to jump to a trampoline. So I put this pointer in the header of the mbuf in exact position. You can be not even 1 byte disaligned. It must be exactly aligned to the pointer. But it's something very easy to do. Okay, let's continue. Yes. Okay. Well, we can now jump to any place of the memory that we want. But where is the shellcode located? We know that the shellcode is located here. Here is a shellcode. It's placed next in the same packet, because it's very easy to put the shellcode in the same packet that caused the overflow. So we got this portion of memory, we got our code, the shellcode or the code that we want to execute. But we don't know where this is placed, because the mbuf are the dynamic align places, and it could be in any place of the kernel memory. It's not in a fixed position. It will change. It will change from run to run and from kernel to kernel. But we know one thing. We know that the shellcode is pointed to the ASI register. The ASI register points exactly where our shellcode begins. Why is that? Well, because that is how the function was compiled. We remember that the packet in the beginning of the function was pointed to ASI, was pointed here. So if the packet is pointed to ASI and we do an immediately jump to somewhere that we want, we must jump to some place in memory that jump back to the position of the ASI register. It's like a bouncing. We bounce in a point of the kernel memory that have an intrusion that jump back to the ASI register. We must find a position of the kernel. This is the kernel. We must find a position of the kernel that got an instruction that jump back to the ASI register. This instruction is a very small instruction. They are no more than 2 bytes long, and it's placed thousands of times in the kernel. So it's very easy to find one instruction. It could be in any place of the kernel. It not only must be there and be executable. So we find one instruction. It could be any. We find one instruction that jump to the ASI register, and we simply jump there. So we jump in this instruction, that instruction jump back to our shellcode, and we are executing our shellcode now. We have complete control of the system. I was thinking, okay, game over, is over, but it's not over. Because, as I was seeing, the kernel, you really can't do anything in kernel mode. I can't even open a file. I can't open a connection to the internet, because I am running in kernel mode. And it's a very tricky. This is a really tricky part to make the exploit works in kernel mode, because it must be like a mini operative system. It should be. Okay, there are a lot of ways to do this, but this is the way that we implemented, and this way really works pretty fine. In kernel mode, there are not many things that you can do, but you can do very easily hook interruption. You can get the interruption table of the Pentium processor, and you can hook. You can make that one interruption to jump to you, and you instead jump to the original interruption. So what I did was to hook this particular interruption, the system call, the operating system communicates with the user process using an interruption in Unix. One in Windows is similar, but in Unix the interruption number used is always the 80 interruption. So I must hook this interruption, the 80 interruption, in the same way that the old terminated style resident program from DOS. In DOS, there were a kind of program, maybe you remember that hooked the interruption, the timer interruption or the keyboard interruption, and in that way it stored resident in memory. Okay, this is the same technique, but we hook the system call interruption. This is the original system call. We got a user process here. The user process make a system call, I don't know, open a file, or kernel open an internet connection, and the kernel open the internet connection and returns to the user in the next instruction. And here is how the hook is made. The system process, the user process, sorry, jump to the hook that I have installed in the memory, and the hook make something that I want, and then return to the original system call, and the system call is made and returned to the user. So the user really don't know if he don't realize that it's calling my call. He thinks that it's calling the kernel, but it's not calling the kernel. It's calling my shellcode in memory. Okay, so it's calling my shellcode. What we do in this situation? Okay, now we can see every system call of the system. We can see every process and every operation of all the process of the system. This is a very useful thing. So I implemented, this is the pseudocode of the operation of the hook, the interruption hook. First, we don't want to affect any user process, because we will, in this way, we will hang the machine. And not every user process are useful to us. Only the privileged user process are useful. The user process with a privilege of root. Because if we take over a process with no privileges, it will be very useful. We want to take over a user process with root privileges. So first, we want to see if the process calling us is root. Of course, this is a very hard thing to do, because we cannot simply get the process ID or the user's ID of the process, because again, we are in kernel mode. We must do a lot of tricks to do this. First, in user mode, you just call system call get PID or get process ID. It's just simply of that. That system call returns a number, and that number says is you are root or not. But now we must do a little magic here. We first search for this variable in the kernel memory, because the kernel can be any kernel. It could be a OpenBSD 3 kernel or 4, or can be a custom compiled kernel. And this variable, the current process variable, in fact it's an array, it's not a variable, could be any place of the memory. So we must search it. We must search through all the memory, searching for patterns, for specific patterns of memory that tell us where this variable is placed. These patterns are present in every OpenBSD version from 10 years ago, and are very easy to find. Once that we got this current process variable, we can see inside this variable, in fact it's a structure, it's not a variable, what is the user ID of the process. So, now we got the user ID of the process, and if the user ID is 0, the process is root, and we can't take over this process. So, if the process is root, we must attack this process. We know that the process has full privilege of the system, and it's much easier to execute code in user land or user mode than in kernel mode. So we got a process that is root, is calling us. We must take over this process. First, we must execute code in this process. We could just overwrite the return pointer. The return pointer of the process should be in because we are kernel, we can overwrite any place in the memory. We could just overwrite the return address But this is not a very good thing to do, because maybe this process, the process that are calling us, the binary that are calling us, is the libc. The libc is a library that is very important in the system. We can't just overwrite the libc, because the system will crash because every process are using the libc. We cannot overwrite the binary. We must place our shellcode in another place. A good place to put our shellcode is the stack, because the stack is one for every process, and it's very easy to reserve memory on the stack, put our shellcode there, and execute our shellcode on the stack. But there is a problem with that approach, that is this protection. This protection is a very good protection that OpenBSD got, that says that no place in the memory that is writable is executable. The memory can be or writable or executable, but not both. So that is exactly what we want to do. We want to write in the stack and execute in that place. So the OpenBSD kernel will not let us to do this. We must disable this protection. This protection can be disabled because we are kernel and we can modify every register of the Pentium processor, because we got complete control. So how we disable this protection? We extend the selectors. The selectors, OpenBSD implemented this protection, changing the selectors and making some selector shorter, some selector larger, and the specific selector that is affecting that it don't let us to execute our code in the stack is this selector, the code selector, of course. We must extend this selector. We extend this anyway. This is not very important, but this selector is very important. We must extend the code selector, or CS, to let us execute code in the stack. This extending a selector can be made in a user process. A user process can extend selector because it don't have permissions to do that. But we are in kernel, so we can extend this selector. Once that this protection is down, we simply copy the user mode in the stack and execute that. We modify the return address to the pointer to the stack, and when the system call is done, it will return to the stack. Instead of returning to the binary image of the process, it will return to the stack. And we'll execute there perfectly because this protection is down. So now we are executing our shellcode in a user process, and it's much easier to do things in that place, like open a connection, or I don't know, adding a user, writing a file. I mean, kernel, because now we are a user and we can make use of the kernel. In the end, of course, we must restore the original interruption vector, because if we don't do this, every root process will be owned, will be take over, and we don't want that, because we want to take over only one process. We only need that. We don't need to take over all the root process of the machine. So we restore or remove the hook, restore the original interruption vector, and that is, now we got one process, the first process that are calling us, root and executing our code. This process could be anyone. Can be the sendmail process. Could be the Apache, I don't know how to say, Apache, the web server. In fact, I was seeing that every time I sent the exploit, the sendmail process was the first that was take over. The sendmail make a lot of system calls, and it's root, and almost every time is the sendmail process is the first that is attacked by this exploit. And if we are not root, if some other process call the kernel and yes, not root, we just continue with the original system call, and we don't modify it, because we are really not interested in attacking a process that is not root. Okay, this is a diagram. We we got a little problem here. There should be a line here and a line here too. This is a map of the memory of the Pentium 32-bit processor and how OpenBSD managed it. We got 4 gigabytes long, and the OpenBSD system reserves the first part of the memory for executing binary code here. So the only executable code can be placed here in this small part of the memory. This could be grow a little. It is viable, can extend a little further, but only this place of the memory is executable, and this place of the memory is not executable, but it's writable. Here is the data memory, the heap and the stack. So this is the operation that we do. We extend the code selector that only reached here originally, and we extend it from to here, all the way to the world memory, so we can execute code in this area too. We also extended the data segment just because it's not really necessary. Well, so a little assembler. This is the implementation of the pseudocode that I was showing. It's maybe a little, it uses some instructions that are not commonly used in user mode, that, like this one and this one, that store global description table and store local description table, because the selectors are stored in these tables that the Pentium processor used to store the selector, let's say. So we first store the selector in some place in the memory, could be any place. We choose to store in the ISP in the stack itself. This section of the code are a lot of operations used to assemble the selector, because the selectors are not contiguous in memory. Are a little, I don't know, like disassembled at some place in 1 byte, and some byte later are other part of the selector. I don't know why this is. The Intel engineers made it that way. I don't know what because, but you must assemble the selector using a lot of Boolean operations. And these two final instructions extend the selectors, place it only a value in a specific place of the memory. Then we must load again the selector. Here is not the part that loads the selectors back into the Pentium processor. It's not shown, but it's next. Okay, but we are not really finished yet. I was saying this exploit is a little complex, because OpenBSD is a clever operating system, and in the next context switch will restore the selectors. So if we are happily executing in the stack, but if the process are context switched back, the process will crash, because the protection, this protection WXOR, this is my WXOR, will be enabled again, and the process will crash. The execution of the shellcode will be detected by the operating system. So we must try to get a portion of memory that are that are writable and executable forever. How we do that? We can use we got 2 options to do that. In fact, we maybe got more than 2 options, but these are the 2 options that I think of. The first one is to use another system call, because I am executing in user mode. I can call any system call that I want, and I call this one that is named aimProtect. This system call is used to give any portion of memory any permission that I want. So I just unprotect all the stack. I say to the operating system that I know I want to execute code in the stack using this, and the operating system just will make the whole stack executable like it was Windows 95, and will be executable forever. We now do a couple of things to fix the original process, because we don't want the same mail process of the web server process to crash. We want to make a new process and to keep the original process attacked to function, to work okay, to work normally. So we first fork the process, make a clone of the process, and now we got two processes that are the same. In one of those processes, we fix all the stack, we fix all the things that we override, and continues to execute normally. So if we attack the sendMail process, we continue to execute like if nothing was happening, and the forget process will be executing our code forever in a secure position of the memory, because we unprotected that memory, and it's over. Now we got a root processor executing our shellcode. There is another way to do this, that is to do another function call that is called mmap, or memory map. We just ask the operating system to give us a special portion of memory that is not in the stack, but is writable and executable. So we just copy our shellcode in that new portion of memory and execute from there. And in the next context switch, there is nothing that can stop our execution, because it's a reserved portion of memory. Okay, and this is the end of the exploit. We are now got a root process executing our code in user mode. This is a sample of what looks like this exploit. Here is a terminal of OpenBSD executing and asking for a login prompt. And I'm sending here the couple of packets. Inside the shellcode, I've inserted a breakpoint of an interruption tree. So this blue part here, in fact, is the debugger of the kernel debugger of OpenBSD. The DDB is called. We can see, maybe you can see here that it's not hanged. The kernel has stopped because it's a breakpoint. It's not a crash. Here, here we ask the debugger to continue to execution, and here the OpenBSD system is continuing with normal execution, but now it's hooked. Now we got all code hooked in the interruption IT. Now I would like to do a live demo of this. I hope it will work. It may not work, but to make it a little more interesting, I'm going to do a live demo. Okay, now we are launching a virtual machine with the OpenBSD 4 operative system, and we're going to launch another virtual machine using the Linux operative system that will send the packet to this virtual machine. The virtual machines are connected together with a host-only network. It's like a virtual network between the two virtual machines. Maybe we're going to have some problems with the resolution. I hope not. I think we're going to have some problem with the resolution. Could you please make the screen a little smaller, because I can't see the top of the screen. I can't move the window. Okay, now the top, please. There you go. Let's see. That is. In the right side is the shellcode. Writing is in Python language. And I'm going to launch the shellcode in the other window here. Okay, here we can see that the OpenBSD kernel has stopped because the attack works, and it's stopped in a breakpoint because inside the shellcode I have placed it as a breakpoint, and we can ask the debugger just to continue with the execution, and the kernel, of course, will be hooked with our shellcode. Now the OpenBSD kernel has a hook in the interruption and is working perfectly normal, like if nothing has happened. But in fact, our shellcode is inside the interruption vector now. Okay, that was one of the live demonstration. But researching about the IPv6 protocol, the IPv6 protocol is not very much used and is active by default in a lot of operating systems. And that is a recipe for a lot of failures and a lot of bugs and vulnerabilities. I will show another ones that I have discovered as a part of my research. Okay, using virtual machines. So we will continue with this. These couple of vulnerabilities are for the Linux operating system. We're going to use the Ubuntu distribution. It's one of the most used distribution of Linux. Okay, this is a Linux kernel, the latest one, the 2.6/22 kernel, and it's a custom kernel, this one. Okay, it's a custom kernel, and I will send a couple of ICMP packets to him to see how it responds. Here we can see it. This is Linux asking for a login. Sorry, this is not. Sorry, I get confused. That was not the attack. This one. Okay. Now we can see that the Linux kernel is hanged. This is because we have sent another couple of IPv6 packet. It's another protocol. But the Linux kernel, you can see as is hanged. I'm going to show you one thing. Maybe you can see the lights are blinking here. This is how Linux kernel for protection is shown. Linux is hung very, very few times, but when it hangs, it just blink the caps lock key. It's very strange to see the Linux kernel hang, but it hangs sometimes. This is a denial of service attack, and in fact, it's not a 0-day, so it's patched. It's patched, but it's in the very latest version of the Linux that is come out, I don't know, a couple of weeks ago. But it's not backported. You mean maybe you have a Linux system over here. I'm gonna to attack a completely actualized Ubuntu system to see if they have patched this vulnerability. Okay, you can see this is a kernel 2.6.20/16. It's the latest one. I have actualized the kernel yesterday at 12 p.m. at 12 midnight, and it was the same kernel. So this is the latest kernel from the Ubuntu system. Okay. Okay, we're going to launch the same library, the same packets. Okay. Well, great. The Ubuntu system survived perfectly. But we're going to launch the first attack. There's some other attack. Oh, damn. So you got there a full patched Ubuntu system that still have a vulnerability. All because IPv6 was activated by default. So this talk is over now, but I want to say only one thing, that is, if you got a Unix system or a Linux system and you got IP activated and you don't use it, please deactivate it. It's pretty easy to do, because you can see there are very bad people out there, and they can do things like this. So thank you. If you have any question, you can ask me now. Sí.
What portion of the packet are you embedding the code?
Well, in the ICMP packet has a data part that is supposed to be replicated in the answer of the ICMP packet. And I place simply in that portion of the packet. It's a big packet, like a 1,000 byte long, and the shellcode, in fact, is something like, I don't know, 700 bytes. It fits perfectly in the second ICMP payload. It's in that part. I could send the exploit in another ways, like, I don't know, flooding the system with shellcodes. The system will place the shellcode any place in the memory. Maybe you're going to fill the memory with the shellcode, and I can't just jump anywhere in the memory, because the shellcode surely will be there. Because if I send, I don't know, 10 megabytes of traffic to the OpenBSD system, it's going to put it in some way, in some place in the memory. Okay. If there's no more question, thank you very much. That's all. Thank you for coming.